Number one, what is the difference between a chemical change and a physical change?
What do you mean?
Yep, review questions, not practice problems.
Oh, I'm on the practice problem.
I know you are.
Oh, you got me.
But we do review questions and then we do practice problems. That's why practice problems are due today. We'll go over them tomorrow. Okay? Review questions were due yesterday. We're going over them today.
Chemical change.
Oh, you have to look it up?
I can't I'm sorry.
Oh, just talk to me. Come on. What's the difference between a chemical and physical change?
A chemical change affects the molecules and atoms.
Okay, good.
And then
It affects them in a way that what? What happens to them in a chemical change? The atoms and the molecules in a chemical change, they
change something.
right, they're rearranged into other chemicals, right? They're rearranged. So we take the physical building blocks of atoms, and in a chemical change, they start as one structure, we deconstruct them and make them into something else. Okay? Physical change.
It changes the appearance of it.
Or change the appearance, or changes how the atoms or molecules sit relative to each other, but doesn't change what they are. So remember, if you think of it as physical is basically appearance, and chemical is changes what we're dealing with in terms of molecules. Not in terms of atoms, but in terms of molecules. It changes what we're dealing with. Okay, that's the basic difference between chemical and physical changes. Number two, but you call it Zach, big surprise there. Got some pathways, your well-worn pathways. And so you have 4, not 3. We skipped 3. Okay, number 2, explain the difference between dissolving and reacting. For example, baking soda dissolves in water, but baking soda reacts with vinegar.
Something dissolves, it kind of just mixes, breaks apart but mixes in, but it's still that, like baking soda is still baking soda in water.
Okay,
It's just broke.
good.
And whenever reaction is it's changing, like baking soda and vinegar, whenever the baking soda reacts with the vinegar, it changes it.
Good. So that's related back to question number 1, right? Dissolving is a physical change. When I dissolve something in water, let's say, or another solute or another solvent, to dissolve a solute in a solvent, the terminology we'll get to later. But when I dissolve something, I'm not changing the molecules that I'm dissolving. Okay? They physically are separated from each other, but they don't chemically change into something else. When I react something, the atoms, or the molecules that are built of atoms, they are breaking down and being built back up into different structures. So in the case of a reaction, break down, build up. In the case of dissolving, physical change, just moving them farther apart. And they're being moved farther apart by whatever they're dissolved in, the solvent. All right.
Completely down to both gags. Got me.
Huh? Okay. Number 4, one type of phase change we did not discuss, however, we did in this class, was sublimation. Sublimation occurs when a solid changes directly into a gas without passing through a liquid phase. Does sublimation occur when something is heated or when something is cooled? Try again.
Heated.
It's going from a solid to a gas, right? Let's think about it in terms of kinetic theory of matter. Going from a solid to a gas. Let's do the hand motions, right? It goes from a solid to a gas. Yeah. Come on, this is a chance for you to actually get permission to behave this way. Okay. So it's going from a vibrating solid to a gas. Does the amount of energy increase or decrease when it goes from to? Energy increases. So the heat had to have, we can use heat energy as a form of energy, right? So we're adding heat to it to make it the motion be greater. So it's being warmed. Remember the direction, think of it in terms of water, not in terms of density, but in terms of the direction of motion, or the direction of increase of energy. What happens? Solid, liquid, gas, as you heat it, as you add energy to it. That direction, solid, liquid, gas, is consistent for every element. Okay? You're always adding energy to go from solid to a liquid. You're always adding energy to go from a liquid to a gas. What changes is the density. Okay? That one has exceptions, but not the direction of phase change when you add or take away energy. Right. So number 5. If a liquid goes through a phase change and all you know is that the molecules slowed down and moved closer together, what phase did the liquid turn into?
Solid.
Okay, so you have a liquid and you're going to slow it down, right? Energy is going to be taken out. Call that cooling. So a liquid cools to become a solid. Every time. Nothing cools to become a gas. It always cools from a liquid to become a solid. Its energy is added to it to take it from a liquid to a gas. Okay. Any questions on what we've done so far? Pretty straightforward, hopefully. Okay, next question. That's good not to know. You have to own it. But first we'll do number 6. What makes water an exception to the phase change rule?
Is it because water weighs more as a liquid?
Okay, a lot of you use that phrase, weighs more. Okay? Weighs more. First of all, in chemistry, we don't care about weight, it's mass. Okay? So if you think in terms of weight, unless you're asked for a force, it's not weight, it's mass, how much stuff you have. The second thing is if I have a sample of water and I have it in a liquid phase and I freeze it, does the mass change? Does it weigh more or less when it's frozen than when it's liquid? Have I lost or gained any matter? No. So the force of gravity on that matter hasn't changed. So if I have a certain amount of water and I freeze it, it becomes an ice cube. It weighs the same as the liquid. It has the same mass as the liquid. If I take that liquid and I add energy to it and I convert it into a gas phase, if I keep control of all that gas has the same mass and therefore the same weight as the liquid. The issue is not the weight. The issue is the density. Because though the mass does not change, the volume does. Okay? And the thing that makes it an exception is not the characteristic. The characteristic is that water is an exception because when it freezes, when it goes to a solid phase, its volume actually increases. Virtually everything else, except for a few exceptions, when it goes from a liquid to a solid, when it freezes, it takes up less space. Water, however, takes up more space. When you take the same amount of matter and you put it in a greater space, you've decreased the density, which is why ice floats. But the technical question here is, what makes water an exception to the phase change rule? Hydrogen bonding. Remember we said that? Hydrogen bonding is what creates this difference where when it goes to a solid phase, it takes up more volume, therefore has a lesser density. That is due to hydrogen bonding, the difference. Most everything goes to a smaller. Water goes to a larger volume. Most everything else becomes more dense as it goes from gas to liquid to solid. It's less dense, medium density, and the greatest density in that continuum, with the exception of water. It's the least dense, it's the most dense, and it's medium density. And that's why frozen water floats and frozen rubbing alcohol sinks. Okay? Clear as mud? Okay. So the characteristics of of a lessening density for a solid and floating, that's all the result of hydrogen bonding. Okay? Hydrogen bonding is what causes it. Oh, this is a good one. Not quite as good as number 9, but what is wrong with this statement? It's passed? Okay. Which means you're not going to get number 9 because you have number 8. Okay. Explain what is wrong with this statement. While substances like CO2 and H2O can exist in 3 phases, it is impossible for metals to become gases.
It is possible for metals to become gases.
Okay. It is possible because it's possible for everything, right? Including metals. Nonmetals, metalloids, transition metals, anything. Add enough energy to it and get the correct temperature pressure combination, and everything can be in any phase. There's no such thing as a pure solid, something that's always a solid or always a liquid or always a gas. Okay? Because everything, if given enough energy, will start to break apart from each other and get more motion. And all the phase is representative of how much motion is taking place. Okay. Number 8. So you have number 9. Congratulations. Number 8. Lead has, I say that only because most people missed it. Just so you know. So number 8. Lead has a density of 11.4 grams per milliliter, whereas gold has a density of 19.3 grams per cubic centimeter. If we have two identical statues, one made out of gold and the other made out of lead, which would be heavier? Okay, talk us through that a little bit.
Just because it has because cubic centimeters and milliliters, they're the same thing.
Right, they're the same units. They're different ways of saying the same thing. So 11.4 grams is being compared to 11.4 grams per milliliter is being compared to 19.3 grams per milliliter, right?
Yeah.
Okay.
Which would make gold heavier per gram. It has more stuff.
Okay, now the phrase for more stuff is more stuff in the same space, right? What's the term we've been using for that? More stuff in the same amount of space.
Mass?
More mass in the same amount of space. Mass per space, grams per milliliter. Density. Okay? It's density. The key here is understanding density. Density is a measure of how much stuff you can pack into a certain amount of space. And I just said a moment ago that you have a gas, you have the same amount of water. And as a gas, it has a certain density. Because all those water molecules you have are in this big space, a big balloon, let's say. A big balloon, let's say that this balloon here was full of water vapor. It has a certain amount of space. But if I were to take the contents of this balloon, and condense it into a liquid, would it take up more or less space? If I take this liquid or the water vapor in here and I turned it into liquid, it would take up a smaller amount of space in a beaker. Okay? So what I've done is taken the same amount of matter, because I haven't lost or gained any water vapor, and when I change its phase, it takes up less space. If you have the same amount of stuff in less space, you've increased the density. If I have two things that are the same amount of space, okay, what this question is stating, and I think you started to say it, I cut you off, so go ahead and finish your logic.
Well, it's just because gold is a higher density. I didn't know if I was supposed to use the word density while I was explaining it.
No, yeah, you can. So since it has a higher density, it means it has more stuff in the same amount of space. Yeah. That higher density, because it has more matter, has more mass, is why it will be heavier, right? Because weight is simply the gravitational pull on the amount of matter. Okay. Derek and I have different weights. Might surprise you. Derek and I do not have the same weight. But it's not because of weight, it's because of mass. Derek and I have different masses because I've got more stuff in me than he has in him. Okay? And because I am made up of more stuff than he is, I weigh more than he does. That's chemistry, that's the way one should think. You weigh more because you have more matter. Now, if I were to take my mass and squeeze it into the same size as Derek, who would weigh more? That's what this question is asking. Think about it. if you take me, who's made up of more stuff, right, and pack it into the same size as someone of a smaller frame, who would weigh more? Me. Because I haven't lost or gained anything, right? I still have the same weight. I'm in a smaller size, but I have more stuff packed into the same size. That's what this question is stating. Two identical statues. The two statues, therefore, both have the same volume. One of them has a higher density. What's that mean? More stuff is packed into it. Because it has more stuff packed into it, it's going to weigh more because gravity is going to pull on it more than the other one. All right? I'm concerned because the only person shaking their head yes is the person who's been absent for more than a week. Okay? So, thank you. Thank you. There's some confirmation there. Any more questions on number 8? Number 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Number 9. A student measures the mass of an object to be 2.32 grams and its volume to be 34.56 milliliters. She then calculates the density to be 0.067129629. There are two things wrong with her value of density. What are they?
I said the number of sig figs.
Okay. Number of sig figs. How many should there be?
3.
3 sig figs. Good, because it's grams divided by milliliters, which would be 2.32, which is 3 sig figs, divided by 34.56 milliliters, which is 4 sig figs. The answer can only have as many significant figures as the least number of significant figures, so the answer can only be to 3 sig figs. If this were right, the answer should have been 0.067. Right? Correct? Okay. What's the second problem? This is where there's a lot of diversity in this class on what the second problem is.
There's
No units.
Oh, wow.
Is it 0.067 grams per milliliter? You would assume so. Yeah, but lacking a unit, we have 0.067 Smurfs. Less than a whole Smurf. Less than a tenth of a Smurf. Like a Smurf big toe. All right? So it's the number of sig figs and the lack of units. That's the answer for number 9. Pass an answer, right? Who has not had a turn? Other than Molly. That would be unfair. Come on. You want to go for it? I mean, you would be answering number, what, 11, right?
Yeah, number 11.
What?
One less chance for me to go.
Sure. Go ahead and send it up. And if she gets it right. No. Number 10. What makes a chemical equation balanced? I can't hear you.
When the numbers of the reactant side match with the numbers of
The numbers of, what do the numbers represent? We say the numbers on one side equal the numbers on another side. What numbers? Okay, so it's the element count. How many atoms, that the number of atoms of each element involved in the reaction, or another way to say it, the count of the atoms, or the number of each atom involved in the reaction, equals the number in the product. Okay, so the reactants and the products. So if I'm counting up, for example, carbons, the number of carbons on the left equals the number of carbons on the right. The number of hydrogens on the left equals the number of hydrogens on the right. So it's based upon the atom count. The number count of each element involved in the reaction is equal for the reactants and the products. That's a balanced equation. Pass it off, and here we go. Number 11. So what law requires that all reactions have a balanced equation? Think about it here. Okay, you didn't have this in class, so think about this. The answer for the last question. Why? What law have we learned that says whatever I have when I start, I have to have when I end?
second law of thermodynamics. The first law. No, okay.
Wow, I got
We didn't cover, okay, the second half says, note, this law was discussed in a previous model. Can anybody in here tell me we've discussed the first or second law of thermodynamics?
No, we haven't.
We haven't discussed this in this class, right? First and second law of thermo. So even though they say we've discussed this law before, many of you gave me laws that we've never discussed before. Maybe you assumed you were sleeping and missed it. Maybe, okay. However, Mr. Jazz Hand,
Law of mass conservation.
for law of mass conservation,
Knew that.
right? He's back there going,
I know, I'm ready.
so you got to wear a hat and go, okay. Right, the law of mass conservation. Why? I have the same amount of stuff in the beginning that I have at the end. I haven't gained or lost anything. To the point where we're talking about, I get down to the atomic level, right? And we know, talk about Rutherford before, right? And all these things, and said, yes, we know today that we can split the atom, but for our class, for our purposes, we don't split the atom. What does that mean? I can break it down to the atom, but I don't break it down anymore. And so if I start with certain atoms, guess what? I better end with the same atoms. All I'm doing is rearranging them when I do chemical reactions. I am not divine with a capital D. I cannot create something out of nothing, and I cannot take something and turn it into nothing. The best we can even argue is I can take energy and turn it into matter, and I can take matter and turn it into energy, but I cannot take energy and turn it into nothing, and I cannot take matter and turn it into nothing. I don't have that authority. Only he, capital H, does. Okay? So realize when you add a subscript in a chemical reaction, you are playing God. And you get a 0 for arrogance. Okay? No, really, that's why the coefficients, God says you can make 2 rather than 1, but I'm not going to let you mess up what's supposed to be made, because that's already set. That's really what it comes down to. Okay? So the law of mass conservation says whatever my atom count for each element before is going to equal my atom count for each element after. And that is, by the question beforehand, what a balanced equation is. Number 12. There's no more, so don't worry about it. Number 12. Explain how a chemist could use the difference method in measuring the mass of a liquid. And we did that. We did it here. Yes, we did. I did it, and I explained it to you. So what is the difference method for determining the mass of a liquid?
Why am I not answering?
Okay. When we worked out the densities, remember I had the 3 different fluids and I poured them all together so you could see them separate out by density? Okay, was that video? The experiment was on the video, okay. So we saw the densities lay out. There was lower, middle, and upper. And I said we were going to, for your lab, I put the numbers on the board so you could use the difference method to figure out the mass, because you're going to need to know the density of each of those liquids to prove that they laid out according to the 3, in decreasing densities from most dense to least dense. So what I did is I went over and I took the mass of the graduated cylinder, then I added the liquid to it, and I took the mass of the graduated cylinder and the liquid together. What is the mass of the liquid? It's the difference method, it's the difference between the mass of the graduated cylinder with the liquid in it and the mass of the graduated cylinder without the liquid in it. The difference is the mass of the liquid. Yes?
You remember the way I worded mine?
No, I don't remember.
I was like, I said you take the weight of the cylinder and then you take the weight of both of them and you subtract the weight of the cylinder. So would that be fine?
Mm-hmm. But it's not weight, it's mass. Right? Because those are 2 different things. No. You're talking, for our purposes, you're talking physics when you talk weight. Physics is forces, more directly the forces. Chemistry, we're talking mass. But I think I gave you credit for it because yet the concept was there. Okay? Break it down a little bit more. What is the mass of the whole thing minus what is the mass of the container? The answer is the mass of what's in the container, the difference method. I also explained to you how to take the volume of something, and it's not on this. Do you remember how we did that? This is part of your videos too. I want to take the mass of something, like those 2 identical statues, right? And you said which one is going to have which is going to weigh more? Well, that weighing more is because it has more mass. That more mass is because it's more dense. Okay? You said they're 2 identical statues. But let's say that we were given the mass and we were told to compute the density of the statue. How would you compute the volume of a statue. Now I told you before, it's real simple if I needed to figure out the volume of a cube, right? All I would do is length times width times height. And I would compute the volume. It's a nice geometric shape that I can use a formula to figure out. But if you've got a nice classic heirloom statue like that, right? The classic heirloom passed down from my great-great-great-grandma. Okay? What's the volume of that statue? How am I going to figure it out?
Well, if you get a cylinder and like pour water in it, you find the volume of that, and you'll put the statue in it, find the volume of that, and subtract it.
Right, it's another difference method, isn't it? Okay? So if I have a volume, if I have a container that has liquid in it, and then I take that same container and I drop Grandma's heirloom statue in it, okay? The difference between the volumes is the volume of the statue. The statue, when I drop it in, do you all agree that when I drop something in this liquid, the level is going to rise? Okay? The amount of volume that it increases is equal to the volume of the statue. And that's how we would do it in this case. So we've got the statue, we get a container, we'd measure the level. What is the volume of the liquid? We would drop whatever we're measuring in it, take the new level, find the difference. That's the volume of the object. The gold nugget question we've had before. You know its mass, what's its density? Have to figure out the volume. What do? Take a container, fill it, read the volume, drop the nugget in, read the new volume, take the difference. That's the volume of the nugget. Okay. Would someone like to request an EPP? Okay. I'll leave it open for a few minutes. Number 2 has been requested. Yes? 13 and 2. 13 is more complex than 2, in my opinion, but I'm just thinking about the benefit of the class. So, balancing. Let's talk through 2 and we'll do 13. How's that? Number 2. Describe what the inside of a container would look like if all 3 phases of acetone were present at the same time. Frankly, that's the way it always is. So what is acetone? How do most of you in here use acetone? Fingernail polish remover, right. So he knows that that's fingernail polish remover. Ladies, where were you in that answer? Apparently, you need to go to him for your cosmetological needs, because he knows acetone is nail polish remover. So, when you open up nail polish, let me ask you a question. Is there liquid inside? Nail polish remover. Is there liquid inside? Yeah. Do you sometimes have a crusty cap on it? Okay. And do you smell it when you open it up?
Oh, yeah.
Boom! All 3 phases are together. Right there. You got the liquid, you got the solid, you got the gas. Now, what does it look like?
Crusty bottle.
Crusty bottle that stinks and has water, fluid in it, right? No. What it's saying is if you have a container and if you could look through that clear container and see all 3 phases at the same time, how would they be laid out? Think about it in terms of the maple syrup, vegetable oil, and water. How did it lay out? It's actually maple syrup, water, vegetable oil, right? So in that situation, that scenario, it lays out from most dense to least dense. I'm not going to give you the answer now, but think of the question. Which phase is the most dense? Which phase is the middle dense? And which phase is the least dense? And you're going to assume within that container, they're going to stack up in that way, right? That's number 2. That's the logic behind number 2. We've got 10 minutes, and I haven't done number 13 yet, so this is a challenge for us together. I'm going to go ahead and kill the projector just so we can get rid of the glare that may be on the video from that. We'll go ahead and do number 13, or you'll do number 13. I'll kind of coach us through it and keep us on track the best I can, because like I said, I haven't done this one yet. And you have not experienced this yet, so put your seatbelt on. Okay? Here we go. And I will get, you're right, number 4 is not up there and number 5 isn't up there. So I will get, I knew number 5 wasn't because I had an issue with the editing, but I'll try to get those up today. All right, balance the following equation. Ammonium chloride plus barium hydroxide reacts to produce barium chloride plus ammonia, phew, stinks, plus water. Okay. If you look at this and you go, that is scary, I should just quit now because I can't do this. First, wimp. Okay. Second, we've gone over the process. Just, if in doubt, go to process and do the stupid process, okay? That's why you learn processes. So when you don't know what to do, you do the process. So pretend you don't know what any of these things are, but you're going to balance this equation. What's the first step in the process? Sir?
Counting up your elements in play.
Identify. Identify first, okay? And I'm not correcting you like firmly. I'm trying to reinforce the process. First, identify before you count. Identify. So I'm looking over here. Looking from left to right, let me identify all of the elements that are in play. So I have, what's the first element? Nitrogen. Second. Third. Fourth. Fifth. Sixth. Okay, so you say that's it. We got to here. Hydrogen, got it. Barium, got it. Chlorine, got it. Nitrogen, got it. Hydrogen, got it. Hydrogen, got it. Oxygen, got it. We're good. Okay, so we've identified 1, 2, 3, 4, 5 elements that are involved. This is not a Lewis dot, so just so you know. Do the count. So we've got reactants and products. Nitrogen count. 1 set of 1. Hydrogen. 1 set of 4. And 1 set of 2 sets of 1. Okay? So I have 4 plus 2 is 6. Okay. Chlorines. 1. Bariums. 1 of 1, and oxygens. 2 sets of 1, which is 2. Product side, nitrogens. 1 set of 1. Hydrogens. Correct, for a total of 5, right? 3 and 2 is 5. Chlorines. 2. Barium. 1. Oxygen. 1. Okay? My process. What am I going to look for? Where I have not used up all my reactants first, right? So where have I not used them all up? Okay, hydrogen and oxygen. Okay. Now, you've got 2 options, right? You could fix either one of these 2. You're going to fix it on the product side, right? Now, which one of these, do either of these only appear once on the product side? Okay, you see hydrogen is in ammonia and water. Oxygen only appears in water. I'm going to go to that one first. Leave the compounds only if you have to. So I'm going to adjust oxygen next. What am I going to adjust oxygen to be? Let's bump it up to 2. Okay, so now that I've made water 2, right? Because I can only add coefficients, no subscripts, only in the front of the molecule. So I make 2 waters now, which means I'm not going to keep this running across the board. Okay, I think you guys get what I did yesterday. I'm just going to go ahead and make modifications right here. So I changed one of the products. Boom, do them all again. A little bit more work, but hey, it's going to be worth it. So nitrogen's on the product side. I still have 1. Hydrogens, What do I have now for hydrogens? Right, 7. I have hydrogens, I've got one set of 3 and 2 sets of 2. 2 sets of 2 is 4, 5, 6, 7. 7. Chlorines, 2. Barium, 1. Oxygens, 2. Okay, now we look for where I've not used up all my reactants, and in every case, we're done, right? Now let me go to my products. Which products, where do I make more than I had? So right here, hydrogen and chlorine. Okay, I'm going to look over here and find out hydrogen and chlorine. Do either of those appear in only one molecule? Chlorine does, so I'm going to adjust chlorine. I need to use up more chlorine. I say I used 2, but I only used 1, so how do I use 2? Smack a 2 there, right? So now since I messed with a reactant, I'm going to erase the reactant column and do the math all over again. Later on, when you're better at this, you can go back and say, all I really have to do over again is nitrogen, hydrogen, and chlorine. Because those are the only things you messed up because of this coefficient. But for now, for process, just do them all again. It's not that long. So nitrogen, I have 2 sets of 1, and that's all. So that's 2. Hydrogen, I've got 2 here, and I have 8 here, for a total of 10. Chlorines, 2 and no more. Bariums, 1 and no more. Oxygens, 2 and no more. First, look to where do I say that where have I not used up all my reactants? Hydrogen. Now I got to mess with 2 of them over there. Okay? Oh, and nitrogen too. But guess what? It only appears in one place over there, right? So let me mess with that one. Nitrogen to NH3. I said I had 2, but I only used 1, so I can fix that by making this a 2. And this is where, when you get a little bit better, you can say, okay, that is going to affect my nitrogen and my hydrogen, just those 2. Everything else stays the same. So my nitrogen count over here is now going to be 2, and my hydrogen count over here is going to be 6 plus 2 is 10. And it's balanced. Okay? So again, starting off, this might have looked intimidating, but if you have a process, just keep repeating the process until you're done. Identify the elements, count up the number of each element in the reactant side, count up each element in the product side. For those cases where you had a certain amount but you did not use them all, increase the coefficients on the product side to use them all up. Once you've done that, go back and look for where you say you've used more than you have and add coefficients on the reactant side to build up the numbers. Keep doing it until everything matches. Save elemental forms and those elements that appear in more than one molecule on either the reactant side or the product side for last. And just keep plugging away until it works. All right?
So the homework is all the practice problems, all the review questions, and all the solutions.
Mm-hmm.
And the lab write-ups.
And then it's on Friday for the lab write-ups, and you have that too. And they've had this for a week, so I know that puts you in a crunch.
What's a lab? Like what is?
You can get the data from your classmates. One of them was, I think, the only video that I did a separate video for the 3 different temperatures of fluid. We put the drop in each one of them,
Yeah.
and one moves fast, one sinks to the bottom, and the other one, the room temperature, slowly mixes. Okay, we did another experiment where we had maple syrup, water, and oil, and poured them together and observed that the maple syrup stayed as a layer on the bottom, the water stayed as a layer in the middle, and the canola oil stayed as a layer on the top. And we hypothesized what would happen. But we also then took the volume and the mass of each one of those, and we said that the way it was going to stack up would be the most dense, the middle dense, and the least dense. But we have actual numbers so you can compute what the density for each one is to prove that that's the way it stacked out.